This is video 54 in our series on tensor calculus. In this video, we'll explore the concept of a physical integral. We'll also show how to employ a multiple integral using any coordinate system to evaluate the physical integral. Let's suppose we'd like to calculate the mass of an object such as the one you see depicted here. Well, to do that, we're going to need a couple of things. First, we're going to need to know the shape of the object or its boundary and dimensions. And we'll refer to that as the physical domain. And we'll use the Greek letter omega to represent the physical domain. The other thing we need is the density. The density is just the mass of the object per unit volume. And that would be a scalar function that could be different anywhere in our domain. It's going to be a scalar function that varies with respect to the position within our physical domain. We usually represent that with the Greek letter rho. So if we're going to calculate the mass, we'd proceed like this. We'd start by imagining a little small volume unit here that we'll call a volume differential, and we'll represent it as d omega. It's just a little infinitesimal chunk of volume here. And it is located at a position P within our physical domain. Now, if we were to multiply this volume differential by the density at that particular point, the product of these two things at this point will be the mass of this volume differential. And then if we repeated the process for every point within the physical domain and added them all together, then of course we'd have the mass of the object. So that kind of an operation for continual mathematics is of course just an integral. So the mass of this object is going to be equal to the integral of rho d omega calculated over the entire physical domain. Now, what you see here is a great example of something we call a physical integral. A physical integral is nothing but the integral of a function of our point in space integrated with respect to our volume differential and integrated over the entire physical domain. Now, the function itself can be either a scalar function, as you see here, or it could be a vector or even a tensor function. Physical integrals are relevant to many applications in physics, including, as examples, the calculation of the total charge, or the center of mass, or the moment of inertia. Now, you'll notice I haven't made reference to any coordinate system, and that's because a physical integral is geometric in nature, and that of course means that it is independent of the use of any particular coordinate system. However, as is typical in cases like this, we will need a coordinate system to actually evaluate specific results. So let's talk about what we do using the Cartesian coordinate system to evaluate the mass. Well, if we did that, we'd start by representing our density as a function of our coordinates, which would be x, y, and z. And then we would integrate this function with respect to one of our coordinate values, typically dx, and we'd integrate it between two limits f1 and f2. Now we integrate it and we pretend that the variables y and z are constants where this integration is concerned. But the limits themselves are going to be functions of these unused variables y and z. So f1 and f2 will be functions of y and z. All right, when we finish with that operation, then we'll integrate that result with respect to the next variable, dy, and we'll integrate it from the limits of g1 to g2, and this time these limits are functions of the one remaining variable, which is z. And finally, we integrate this result with respect to the final variable of z, and the limits from h1 to h2 are now going to be constants. Now, typically one of the most challenging parts of this process is choosing these limits. They have to be chosen very carefully to match up and represent the boundaries of our physical domain. Alright, well, I expect that you have seen a process like this in your early days in calculus. This kind of operation is known as a repeat arithmetic integral, or more commonly known as a multiple integral. It's something you might want to go back and review on your own using your own resources. Now, all of that is well and good, but in the spirit of tensor calculus, we certainly don't want to be limited to the use of Cartesian coordinates. So let's branch out onto a separate line of analysis to derive an invariant expression that'll work for any coordinate system. Here I've defined three vectors. We've got vector A. It points in the direction of the z1 basis vector and has a vector component of dz1. And then vector B points in the direction of basis vector z2 with a component of dz2, and vector C points in the direction of basis vector z3 with a component of dz3. So over here I've shown what this looks like when we organize it in a diagram. We have vectors A, B, and C that point respectively in the direction of basis vector z1, z2, and z3. Alright, now let's draw some lines parallel to each of these vectors to complete the figure and form a parallelepiped. Now you'll probably remember we did this back in video 52, and when we did, we discovered that the volume of this parallelepiped could be represented this way. The volume, a scalar value of the volume of this parallelepiped, is going to be equal to A, vector A, dotted with the cross product of B and C. What we said back in video 52 is that the magnitude of the cross product of B and C is the area of the parallelogram, that's the base, and then when we dot it with A, that effectively multiplies by the height of the figure. So this is the expression that gives us the volume of this little parallelepiped. Okay, well, in tensor calculus, we'd represent it this way. Our volume would be equal to A dotted with the cross product. Well, the cross product was epsilon I, j, k, b, j, and ck. That's the cross product of vectors B and C. And to dot it with vector A, we need to multiply by a figure here, this factor of AI, which forms a contraction using index I. So now we have a full contraction, and that forms a scalar value. Well, of course, these are just factors multiplied together. We can change the order of them, so let me do that for convenience. Our volume then is going to be epsilon I jk times A, I, bj, and ck. And of course, don't forget, we're talking about an invariant expression here. We've got all of these factors are tensors, so this is a tensor product, and we have a full contraction. Each of these indexes is a dummy index, so it all contracts to be a scalar value, and that scalar value is invariant because we're dealing with a tensor equation. Now let's use this expression and substitute in the values as per the definitions of our vectors. So as we expand this out, remember that because of this Levi-Civita symbol here, although the full contraction would represent 27 terms, all but 6 of them are going to be 0. It's only the terms in which the indexes I, j, and k represent some permutation of the values 1, 2, and 3. So we've only got 6 terms we need to work through here. So the volume of our figure here, we'll start with the first term, epsilon 1, 2, 3, times A1. A1 is the first component, the one component of vector A, which is dz1. And then Bj would be the second component of vector B, which is dz2. And then the third component of vector C, which is dz3. Okay, that's our first term. So let's form the next permutation, would be epsilon 1, 3, 2. Now here we're going to have the A1, which again is dz1. And now we'll have the third component of B, this is B3, but the vector B only has component 2. Because it's parallel or pointed in the direction of basis vector 2, it has no component 1 and no component 3. Those are both equal to 0. So B3 is equal to 0 here. And likewise, the second component of vector C is 0 because it's only got a component pointing in direction 3 here. All right, next term, epsilon, what do we have? 2, 1, 3 this time. And here we've got A2. Well, for the same reason, this is 0. A only has a component in the one direction. And then we have, let's see, B1. Well, that's also 0. And we have C3. Well, that's dz3. Okay. And the next permutation is epsilon 2, 3, 1. Well, A2 is 0. B3 is 0. And C1 is 0. The next permutation is going to be epsilon 3, 1, 2. And A3 is 0. B1 is 0. And C2 is 0. And the final permutation is epsilon 3, 2, 1. A3 is equal to 0. B2 is equal to dz2. And C1 is 0. Okay, we went through all of that to see that every one of these terms has at least one factor of 0. In other words, the entire expression is equal to this one term. The volume of our parallelepiped is simply epsilon 1, 2, 3 times dz1, dz2, dz3. So now let's remind ourselves of the meaning of epsilon 1, 2, 3. Well, by definition, that's equal to our volume element, square root of z, times our permutation symbol, E1, 2, 3. And E1, 2, 3 is just equal to 1. So epsilon 1, 2, 3 is simply the square root of z. So now finally we can write the expression for the volume of our parallelepiped this way. The volume is going to be equal to the square root of z, plugging this in place of epsilon 1, 2, 3, and then times dz1, dz2, and dz3. All right, so what we have here is an invariant expression. Let's not forget that V here is invariant because of this relationship up here. We know it's invariant, and we just plugged in the values as we defined vectors A, B, and C. And so this is an invariant expression that works for every coordinate system. Okay, well, if it works for every coordinate system, then of course it has to work for Cartesian coordinates. So what would it be there? Well, the volume element for Cartesian coordinates is just 1, and each of these differentials is simply z1, z2, and z3 are just x, y, and z. So this is equal to dx times dy times dz. And that, of course, is what we referred to in our previous discussion as our volume differential d omega. So what we now have is an expression. This expression right here is equal to our volume differential. And it is an invariant relationship. It works for every coordinate system. Now, don't miss the fact that this works because of this factor right here. This factor, the square root of z, acts as sort of a conversion factor to ensure that each one of these combinations of factors will result in an invariant expression for our volume differential. With that, I think you can now see why we refer to the square root of z as the volume element of the coordinate system, because it is useful in making sure that this kind of relationship remains invariant. Now that we have an invariant expression for the volume differential, we can generalize the evaluation of our physical integral. We have the integral of a function f with respect to our volume differential integrated over the entire physical domain. We're going to evaluate that as a triple integral of our function f expressed in terms of z, which is the coordinate system of choice, multiplied by the volume element, which is the square root of z, times dz1, dz2, dz3, and of course we'll integrate this over the entire physical domain. Which means, of course, we have to choose the appropriate limits for each of these three integrals to represent the boundaries of our physical domain as they relate to our particular coordinate system of choice. Okay, so what we have here then is the invariant expression we need to evaluate a physical integral. So let's finish up with a simple example to show how this works in real life. Let's apply what we've learned to find the volume of a sphere. Here we've got our sphere as our physical domain, and we're going to perform a physical integral when using the function of 1 here. So if we use the function of 1 there, then what we're going to get with this physical integral is just the volume of our physical domain. Okay, now if we do this using Cartesian coordinates, this is what it would look like. We would have this as our volume differential, and then we'd have to apply each of these limits to our repeat arithmetic integration. Now, these limits are necessary because it limits the way that x moves back and forth from one edge of the boundary in our physical domain to the other. And of course, since it's curved, we have to have these formulas to tell us what the limits of x would be. Well, this is soon going to turn into a much more complicated expression, because when we differentiate with respect to x and apply these limits, the next integration is going to involve an integral of this radical, which is a little bit involved. When we're done with that, we have to substitute in these limits and then integrate with respect to z. And so there's a lot more algebra and uncomfortable integration here than we'd like to deal with. So instead, let's choose a better coordinate system. Let's choose spherical polar coordinates for our example. And there we'd have the volume is equal to a triple integral. And this time we're using spherical polar coordinates. And if you look back in video 48, you'll see that the volume element for spherical polar coordinates is just r squared sine theta. So as we develop our volume differential here, we start with the square root of z, and that's what this is. And then we have our differentials, dr, d theta, and d phi. Now here the limits are much easier to deal with. For r, the value of our little integral, it moves from the origin out to the edge of the shell, so the limit here is just 0 to r. And then theta is the variable that sweeps from the North Pole down to the South Pole, so it varies from 0 to pi. And then phi is the little door that swings from here all the way around, so it varies from 0 to 2 pi. Okay, so the same problem of finding the volume looks like this in spherical polar coordinates. Okay, now the first integration is going to be with respect to r, but before we do that, any factors that are independent of r that do not depend upon r can be treated as constants and can be moved outside the integration here. Likewise, any factors that don't depend on r or theta can be moved all the way out of the second integral as well. So we can do this. We can say that v is equal to the integral of d phi, integral of sine theta, d theta, and integral of r squared dr, putting the limits back on it like this. So all I've done here is you can see that this factor of d phi doesn't depend on r or theta, so it can move all the way out here. Sine theta and d theta can move here and leaves us with just r squared dr here. Now, the benefit of these nice limits is that they're all constant. Normally we'd have to integrate this last term first, apply the limits, and it would be, the limits would be a function of theta and phi, and we'd have to then do the next integral and so on. But because all of these limits are constant, we can do these integrations in any order we like to, because the limits are going to be such that none of this is going to depend on theta or phi, and so each of these are independent integrals. So we can actually do all of them at the same time. So we'll do that. So the integration of d phi is simply phi, and we'll wind up applying the limits here from 0 to 2 pi. And then the integration of sine theta d theta here is just minus cosine theta, and the limits are from 0 to pi. And then the integration of this last with respect to r is just 1/3 r cubed, and the limits again here are 0 to r. All right, we'll apply the limits across here. Limits, this one, 2 pi minus 0 is just 2 pi. So that's the first expression. Negative cosine of pi will be 1, and then plus cosine of 0, which is 1. So applying the limits here just gives us the number 2. And then here we have 1/3 r cubed minus 0 is just 1/3 r cubed. And then when we collect all these factors together, we get our expected answer of 4/3 pi r cubed. And so finding the volume of a sphere is just this easy as long as we use spherical polar coordinates. Now, this problem is a great example of the technique we described all the way back in video 1. If you remember, there we said that our strategy is going to be to avoid committing to a particular coordinate system as long as we can. And when we're finally forced to commit to a coordinate system, we want to make sure we pick the right one. In this case, spherical polar coordinates is clearly the correct choice. What we did in this video was to develop an invariant expression for the volume differential. Our volume differential is equal to this expression, and that applies equally well to any coordinate system. Now the key that makes this work is this factor of the square root of z. You'll remember we defined that as the volume element, and now you can see why. It is the conversion factor that's included with this expression to ensure that we get identical results regardless of the coordinate system that we choose. Now we then went on to use this expression for the volume differential to show how we can perform a physical integral by using a repeat arithmetic integral like this. And because we have this invariant expression, we can use it here, and that lets us evaluate the physical integral using any coordinate system that we choose. And with that, you should have a pretty good understanding of the physical integral and how to evaluate it.